And now we're going to shade the, Now we're going to shade the nonmetals. Am I finished shading the nonmetals? No, what have I forgotten? Hydrogen, very good. Don't forget hydrogen. Metals and nonmetals also have characteristic properties. What is a property? Aspect, characteristic, something like that. You are responsible for memorizing these. We're going to have a quiz on this next Wednesday. Now, metals and nonmetals, you actually don't have to think too hard. Some of them are pretty straightforward. If you look at most metals, what do they look like? They look shiny, shiny, skinny. Aluminum's metal, yep. And nonmetals are generally dull. So if you look at your pencil lead, what's your pencil lead made of? Carbon. Is it shiny or is it dull? It can have a little bit of a sheen, but is it shiny in the same way as a metal? No. So we call them dull, although you will see a little bit of a sheen to things sometimes. It's not the same as that shine of a metal, yeah. Okay. Think about all the metals you know. What state are they at room temperature? Solid. Did you have to think about that very hard? No. You should know the exception. Mercury. And mercury is, of course, a liquid. At its freezing point, I don't know what the freezing point is. We could look it up. Although everything seems to take a long time on this computer, so maybe if someone wants to look it up on their phone, you could look up the freezing point of mercury and let us know. I don't know. Oh, the old thermometers. Usually the problem with the thermometer is that you put it in something that's got a too high temperature and it bursts. When I was a kid, I did that once, the old mercury thermometer. And then I just rinsed it down the drain because it was over the sink. You know, I was a child, I didn't know what I was doing. Negative 38, yep. Now, everyone likes to think, I often have students come in and they're like, oh, the metals are solids, the nonmetals are gases. That is not true. Some of the nonmetals are gases, but as we were just talking about, what about carbon? Is that a gas? No. How many people have seen the sulfur piles down in Port Moody, those big yellow piles of, nobody? One person, maybe. Probably. Here, let's look them up. Even though I said I wasn't going to look something up, but we'll look them up. It's near Rocky Point Park. Yeah. There we go. Okay. So that's why it smells bad in parts of Port Moody, is because we have these piles of sulfur, like big piles of sulfur. You can see there's a man walking there. All right. And it is obviously not a gas at room temperature or at, normal temperatures. It is very obviously a solid. Okay. So some elements, some nonmetals are also solid. Where do those nonmetals that are solid tend to be, do you think? Like where on the table? They're closer to that barrier with the metals, okay? So the ones that are solid are closer to the staircase. The ones that are gases are further from the staircase. And then we have one exception. Who is that one exception? Bromine. You should also know this exception. Bromine is a liquid at room temperature, okay? Density. Are metals dense or not very dense? It does depend on the metal, but compared with, say, nonmetals in general, they are fairly dense. No, aluminum's not very dense. It's also higher on the periodic table. The lower you go on the periodic table, the more dense they become. But in general, metals are dense, and in general, nonmetals are low density. Have you heard the words malleable and brittle before? Okay, so if I hit something with a hammer, you are responsible for knowing the actual word. So if you have, if you have trouble remembering words, write down malleable. It's mal, and then e, and then able. Okay, mal, e, able. Okay, malleable. Malleable, if you hit it with a hammer, it just deforms, it flattens out. Okay, it does not break. When I was a child, so many things that I did as a child you shouldn't do. Okay, that mercury down the drain thing was not a good idea. Okay, but I was young and stupid. I was like 8 or something, right? Oh. We would go up to Shuswap Lake, sort of north in BC, more north than here in BC. And there's railway tracks by the lake. And we would take a penny. Do you guys know what pennies are? Yeah, okay, just checking. And we would take a penny and we would put it on the railway track. You're really not supposed to do that. It's not good for the wheels. It's not good for the track. But we didn't know any better because we were kids and we were stupid. So we put the penny on the railway track and we would wait and the train would go by and then we'd go look afterwards and our penny was still intact. It was just smooshed. No, 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 yeah. Okay, so don't do that. It's really bad and it can cause damage to the wheel and the train. But like I said, we were young, we were stupid. I don't know, again, around 8, maybe 9, I don't know. Children, they don't know very much. Okay, so that is malleable. But what happens to your pencil lead if you hit it with a hammer? It breaks. And when things break, when you hit them with a hammer, we call them brittle. Brittle. Have you heard of peanut brittle? Peanut brittle is, I don't know, I think it's a very overrated sort of food item myself. I find it's a little bit just too sweet and yeah, but it's basically like caramelized sugar with peanuts in it and it breaks when you hit it with a hammer. Ductile has nothing to do with ducks or ducts. It means that you can stretch it into a wire. I used to remember this when I was in high school because like in our basement our ceilings were exposed and in the ceiling you could see like the wires and you could see the ducts. And so to me in my mind the ducts and the wires went together And so I was like, oh, can be pulled into a wire? That is ductile. Copper wire, you can make gold wires, very expensive. I mean, you can make a wire out of just about any metal, it's just that some of them won't be particularly useful. If you make it out of sodium, then it's going to just, anytime it comes in contact with any water, it will burst into flame. So we don't tend to do that. Copper is, yeah, that's why most of our wires are made out of copper, yeah. Gold might be the most efficient, but you're not making things out of gold because it's expensive. Yes. Why is gold expensive? Just it's harder to come by than some other metals. And it's also like, I mean, why are diamonds expensive? Diamonds should not be expensive. It's just that they've made an industry out of it. Do you know what I mean? It's honestly, if it were up to me, the diamond industry would just be like out of business because I find it just gross that people are making all this money out of these things which you could actually get quite cheaply. So whatever. It might be harder to have that perspective, but I think I would work hard at having that perspective. Do you know what I mean? Like there's things in life where I'm like, oh, I would like to do this. I would really like to do this, but I'm not going to do it because it's not the right thing. But, you know, I'm not a good enough person that I feel awesome about that. You know, there's those really good people who feel really awesome, like doing the right thing. Whereas I feel, you know, somewhat of a sense of disappointment, but, you know, I've done the right thing, so okay. Anywho, anywho, ductile, able to be pulled into wires. Conduction of heat. What are your pots and pans at home made of? Metal, usually. Back in the 1980s, there was a phase where they had like these pots and pans that were made out of glass, but everything took forever to heat up. And you'll notice, like, if you're baking a cake, they're like, if you have a glass pan, you need to cook it this much longer. Yeah? And that's because the glass, which is made of silicon, a metalloid, and oxygen, a non-metal, it does not conduct heat nearly as well as a metal pan. And so that's why if you have a glass cake pan, you need to cook your cake for longer than if you have a metal cake pan. Okay? So conduction of heat, metals are good, non-metals are poor. Conduction of electricity, our wires are made out of metals, they are not made out of non-metals. So, yeah. So you are responsible for memorizing this table, knowing the identity of the two elements that are liquids at room temperature. And you are responsible for knowing the definitions of malleable, ductile, and brittle. I'm not going to have you do this now. Sorry, there was a question. Yes. I think as long as you know the one, it's okay to just be like non-ductile. It is the opposite. Yes. Okay. I'm going to let you do this one on your own. This is just kind of for practice. It just gives you a place to practice, but you can do that later. Okay. There is a third category of elements. They are the metalloids. Have you heard of the metalloids before? Yes. Where do the metalloids fall on the periodic table? Right next to the nonmetals and next to the metals. They are on the staircase. And in fact, if you look at that periodic table over there, what color are they? They are purple. Okay? Most metalloids, they look like metals. They tend to be shiny, but they're less conductive. They're more brittle than a metal, so if you hit them, they'll tend to break. They are typically solid at room temperature, just like those nonmetals that are close to the staircase. And this is one that is important for our next unit when we're looking at compounds. They tend to form covalent compounds. So covalent compounds are mostly made of nonmetals, but also metalloids. So when we get into saying ionic compounds, metal and nonmetal, covalent compounds, nonmetal, nonmetal, and then people are like, well, where do the metalloids go? Where do they go? They go with the covalent compounds. The metalloids all border the staircase except aluminum, which is a metal. And I think you guys know that aluminum is a metal. That's not hard, right? Aluminum foil, you look at it, it's like, oh, that's a metal. So here they are. What do you notice happens down here? They just kind of like, yeah. Do you know why? Because the atoms down in this bottom section here, not all of that, but like these guys down here, they're very, like they're man-made. They're made in particle colliders, and they exist for microseconds. So how are we going to sit there and look at their properties? Ooh, can I pull it into a wire? I don't know. I only have one atom of it at a time, and it exists for 3 microseconds. Do you know what I mean? Like, how can you possibly look at the properties of these and decide, is it more metallish? Is it more non-metallish? What is it? These elements just don't exist long enough. In order to, they're not stable, okay? They're very radioactive. You can do them by smashing atoms together. They can bind together in a nuclear reaction, but that atom is so unstable it will break down into smaller atoms. And so studying them, not so useful. So people are always like, well, what happens after polonium? What is astatine one? Is this LV one? I don't even know what LV is. You know what I mean? Like, I'm like, I don't know. LV, liverinium, I don't know. Anyway, what's TS? I don't know. OG, I can't even read that. Okay. These guys down here are man-made. They are unstable. Because why do we go to the moon? There's no actual point in going to the moon. Do you know what I mean? Right? Like, but and like why are people going into space like just like, you know, Elon Musk and things like that? It's not like they're doing much useful up there. They're just sort of having fun, which is fair enough. We're learning, you might be learning things about atoms. I don't know enough about particles physics to know what they're learning. Probably, but not very much. And it's probably all in a lead-lined container, lead blocks radiation. Nuclear stuff, yeah. Yeah. But they're doing it, I think, in really small quantities. Right? Yeah. Okay, you don't need to know about tennessine, astatine, oganesson. There is one thing that you need to know about metalloids and their properties, other than just kind of knowing they're in between. You don't need to memorize their properties. But there is one you need to know, and that is that they are semiconductors. And why am I making you memorize the fact that metalloids are semiconductors? It's because it is completely and thoroughly important for the computer industry. Your cell phone without silicon would not work. Have you heard of Silicon Valley? Not heard of Silicon Valley. It is down near San Francisco, San Jose, California, and it's sort of where the tech boom of the early 2000s started and was at its biggest. Okay, and your computers, your cell phones, all of those things are based upon the semiconductive properties of metalloids. So I think it's important enough that you should be like, ooh, metalloids, semiconductors. Okay, that's all you need to know though. And when we get to the naming and formulas unit, you should remember to treat metalloids like non-metals because they tend to bond covalently. Okay? That'll be our next unit. All right, let's see where we're at here. Yeah, okay. So you could do whatever's in here. Yeah, why don't you just take a few minutes and fill in the table once, leave the other one to do later. Okay, so do this one. Actually, you can go back and you can do number 1 and 2, or 2 and 3 rather. Page 66, number 2 and 3. Page 68, number 4. Page 69, do all. Uh-huh.
So it's just like this plus, I don't know, this. It's
Uh-huh.
just going to be 480.
Yes. Yeah. We are going to learn something else.
But that's also like skinny at the same time. They have a massive fat person. So they're skinny, so the cross-sectional surface area is low, so their terminal velocity is quite high. And they're wearing skin too. Someone who's like exceedingly heavy. That's the way. Like think of like someone. I could. Yeah, but we're. Yeah. I mean, have to reduce cross-sectional surface. I think we're really doing that.
Okay. So we are now going to go on to 3.5. Oh no, 3.4b. Page 70. Lewis structures, which are just scaled down Bohr models, okay? Did you guys do Lewis structures last year? Some of you did, some of you didn't. Okay, so we're just going to pretend you've never heard of them before. So totally fine. They only include the valence electrons, okay? Basically, we just get rid of the circles and we only include the valence electrons. They're called Lewis dot structures. They can be called Lewis structures. They can be called Lewis dot diagrams, electron dot structures, electron dot diagrams. So many names for just one thing. I'm going to call them Lewis dot structures because that's what I grew up calling them. And yes, oh yes, thank you. To turn a Bohr model into a Lewis dot diagram, basically, you don't draw any of the protons and neutrons in the nucleus. You just replace it with the symbol. Okay? So much easier already. And then you get rid of any inner shells and you only leave the outer shell. And then you get rid of the circle and you just draw the dots. Now, it gets even easier because you don't even have to you don't want to be drawing the Bohr model and working your way to the Lewis structure. But do you remember we went through the periodic table and we said we know how many valence electrons are in group 1? How many valence electrons are in group 1? Oh my God, how many valence electrons are in group 1? 1, okay, thank you, okay. Right, so you go, oh, if I have lithium, which is in group 1, I put 1 electron on it. Does it matter whether I put it at the top? Does it matter if I put it at the side? Does it matter if I put it at the bottom? That one looks a little weird. I probably wouldn't go for that if I was just drawing it on its own, but it's not really wrong either. Okay, any of these would be fine, and that would be the same structure for sodium, for rubidium, for potassium, for any of the alkali metals. They would all just look like that. Okay? So basically just figure out the number of valence electrons and then place them top, right, bottom, left, one at a time, only pairing up when you have to. So if we have oxygen, oxygen is in group 16. So how many valence electrons? 6 valence electrons. So we've got our oxygen and then we go 1. Where do we put the second one? On the right. 2, 3, 4, 5, 6. And that's oxygen. Would it be okay to draw oxygen like this? Yep. Okay. I just like to go around like a clock because it makes my life easy, but you can move those electrons And when we start using these to show bonding, you might want to move those electrons from one side to the other just to make the structure fit a little bit better, okay? But that's really it for this. You figure out how many valence electrons and you throw dots on them, okay? Let's see, in a Lewis structure, we are drawing the electrons in the valence shell, which is slightly different from the valence electrons. Electrons in the valence shell versus valence electrons. Different, slightly different. Don't get too wound up about the terminology, but if you look at a noble gas, do you remember your noble gas? Let's say we have neon. It has a full outer shell of 8 electrons. So it has 8 electrons in its valence shell, but how many of those electrons can be involved in bonding? None of them, so it has 0 valence electrons, even though it has 8 electrons in its valence shell. Don't worry about those terminologies too much. I'm not going to ask you questions like that. I'm just going to say how many valence electrons, and I probably won't ask you about a noble gas. Valence electrons, remember they refer to partially filled valence shells. But like I said, don't get too worked up about it. All it means is that even though neon technically has 0 valence electrons, we still draw all the dots for it to show that it's full. Okay? And that's it for that. So you can practice drawing Lewis dot diagrams for the first 20 elements on the periodic table. Woo! Okay? Now, technically, the orbitals are all slightly different energies than each other. Not all, but like when we get into, you remember we were looking at the spheres and then like the two that look like this? The sphere is at a lower energy than the two balloons. Just slightly lower. Why? I'm sorry, that is what it's called. I have no control over that. That's its name. There was a good question about helium. Helium, we're going to put 1, 2 electrons together, okay? Because we're filling up that shell, they're going to pair up, okay? So your homework, finish off what you were working on earlier, read page 72 and do page 73. I'll put that up on Teams. Okay? Yes, definitely. It'll be up on Teams. Hi. Oh yeah, help yourself. Um, what I'd like to do is I'd like to arrange for one day after school next week and everybody can do it so I don't have to stay after school like on for different days. What day would be good for you? All right, so it's probably going to be either Tuesday or Wednesday next week. We'll talk about it tomorrow instead of Monday. Okay. Same question. I'm thinking either Tuesday or Wednesday next week after school. Yeah, absolutely. Please do.
I don't know how to study it.
That's okay. Come and I can help you. Okay? Yeah. Hi. Yeah, and in fact, if you only want to rewrite that section of it and you're like, I'm happy with my math, you can leave that part alone. Yeah, then you don't have to be like, oh my God, I have to do all that math again.
My math is good, and then
Yeah, and like having to do that at the same time, I think it'll save you and me some grief,
I was
right?
mainly worried about the math and
But you know what? Like the fact that you did such a good job with the math, because I know for a while it was like, but then it obviously all came together for you. Yay! So that's good. Okay? Yeah. Yeah. Yeah, something like that. We'll set some dates tomorrow and we'll talk to sort of everyone about it and see if we can set up like one or two after school next week.
I really need
Yeah.
I want to record that on my report card hopefully before.
Well, it won't go on your report card because my marks are due on Monday. But you can let your parents know if your parents are wound up with it. But this is just my snapshot. And I'm doing this year. So, hello. Oh, thank you. They're from Africa. Oh, they were okay. Unfazed. Unfazed.